Let me. Okay, let me bring this up. So assignment, let me mute this here. Okay, so assignment number 7, we're continuing, and I completed everything up to number 2, I think it was. So we're going to look at number 3 now. And number 3 is asking for you to calculate the standard EMF of this reaction along with its delta G standard and K value. And again, you're going to need a table for this. I already worked this out in order to save time so that we can expedite this here. All right, so the first thing I would do is I would separate that equation into the relevant 2 half equations, right? So what I did was that I went on, I looked up the EMF values for the half equations that we'll be concerned with. And this is what I have. 2 mercury 2 plus 2 electrons to give mercury 2 plus. And when I looked up the standard EMF value, that is 0.92 volts, right? And then the other half equation is the reduction of gold 3 plus 3 electrons to give gold. And the standard EMF value for that is, when I looked it up, 1.40 volts, right? Now, of course, you have to identify which one of these 2 would represent the anodic or the cathodic reaction, right? And the one that is most likely to occur based on comparing these 2 EMF values would be this one. So this is the reduction reaction here, and this would happen at a cathode, right? Which means that this reaction here, or the EMF value here, would be for the anode, all right? And therefore, this reaction would actually be reversed in practice compared to this one right here. So therefore, the standard EMF of the reaction, which is what the question is asking for here, if you remember from the examples that we have worked, it's the EMF of the cathode minus the EMF of the anode, standard in each case. So that would be 1.40 volts minus 0.92 volts. And when I did that calculation, I got 0.48 volts, right? So that's the first thing that we solved. Delta E, I mean not delta E, E standard. And the next question is asking, let me just draw a line here to separate that, is delta G. Delta G standard would be equal to minus NF standard EMF, right? Remember, N is the number of electrons that is transferred between the 2 from the cathode to the anode, right? Now, because you have a 2 here and you have a 3 here, that means you'd have to multiply this one by 3 and you have to multiply this one by 2 so that the number of electrons lost and gained would be 6 electrons. So this would be minus 6 times Faraday constant, which is always 96500 coulombs, multiplied by the standard EMF that we calculated earlier, which is 0.48 volts. And that's it. Where's my calculator? Oh, I think I did it here. So when I did that calculation, the answer I got, oh, by the way, I just realized something. Okay, this should be minus 0.48, and let me tell you the reason why. If you look at this equation here, right, you'll notice that the gold and the mercury 2 plus is on the left side. The mercury 2 plus is, hold on. So that's, right. The mercury 2 plus and the gold is on the left side, right? Now, in this equation here, the mercury 2 plus is on the left side, but the gold here is on the right side. So you'd have to turn that around. So this should be minus, hold on. Okay, so let me take out this minus sign here, all right? Everything is all right. I don't know what I was thinking. So this would be, according to my calculations, this should be minus 2.78 times 10 to the 5 joules, all right? So that should be the value for the free energy of that reaction, all right? So that's the delta G part. So for the K part now, remember delta G standard is equal to minus RT ln K. So K would be equal to E to the minus delta G over RT, which would be E to the minus delta G, which is minus 2.78 times 10 to the 5 joules, divided by R, which is 8.31 joules per mole Kelvin, times the temperature, which is 298 Kelvin. All right? And by the way, this here should be joules per mole, because this should be coulombs per mole. So this should be joules per mole here. And when I did this calculation, I got 112 e to the 112. And I made a mistake on this paper right here. So let me do this here. So I have to calculate what e to the 112 is. And according to my calculation, that works out to be 4.4 times 10 to the 48. And that would be the answer for A. So 4.4 times 10 to the 48 would be the answer for K. And that's basically how we answer that question. Okay, any questions about this one? Any questions? Any questions out there in Zoom? Okay, and I think, if I'm not mistaken, that is the last question. Yeah, that's the last question in this assignment. All right. So what I'm going to do now, oh, yes, ma'am, sorry.
Also put it in addendum.
Oh, right, yeah, but, okay, yeah, but we have to cover some topics first before we
Okay,
get to
I
that,
wasn't
yeah.
sure.
Right. Yeah, there are more questions actually, but, you know, as you said, we have to do some electrolysis type concepts covered first. Okay, so let me clear this. And now we're going to go back to the PowerPoint, and we're going to talk about electrolysis. So, as I said at the beginning of this chapter, I said that there are two types of electrochemical reactions we'll be looking at. The first type, which we were looking at all this time so far, are reactions where they are spontaneous and they produce an electric current, right? What we'll be looking at now are reactions that are driven, reactions that are otherwise non-spontaneous, and therefore you'd have to basically use energy to drive those non-spontaneous reactions, right? So basically what we'll be talking about is electrolysis, all right? Electrolysis is basically what I just said, using an electrical energy to drive a non-spontaneous chemical reaction, all right? So here's an example of such a process. What we're talking about here is the electrolysis of sodium chloride. Sodium chloride, of course, is an ionic compound. And you can electrolyze sodium chloride. By the way, when this term electrolysis, let me just say this first. So in chemistry, and this is for future reference, whenever you see any term ending with lysis, like electrolysis or homolysis, heterolysis, you know, basically what that means is that you're breaking up something, right? So, you know, in the case of electrolysis, you're using electric current to basically break up sodium chloride, which is an ionic compound in this particular example, breaking it up into its constituent elements, right? Now, there are two forms of sodium chloride that can undergo electrolysis. You have the sodium chloride in an aqueous solution, or you have molten sodium chloride. Molten is basically a term that is used to describe substances that are in the liquid state, but can only achieve the liquid state under very high temperature conditions. So the melting points for these compounds are very high. And that is certainly true in the case of sodium chloride, right? Okay, so in both cases, what happens is that the ions are free to move around that. Ions are very mobile, right? So therefore, when you apply a potential difference to electrodes, then basically the ions will migrate to their respective electrodes, all right? And what is shown here is in the case of molten sodium chloride, right? So this yellow stuff that you see here is supposed to represent molten sodium chloride. And you have the electrodes, this is the iron cathode, right? And you have the carbon anode, right? The anode is positively charged and the cathode would be negatively charged, right? And what happens is that the sodium ions from the sodium chloride will undergo reduction at the cathode, right? And that's the equation right here, right? The sodium ions will pick up 2 electrons from the cathode to form sodium, which would be also in the liquid state. So therefore you see the liquid sodium being shunted off and collected elsewhere, here and here, right? And then now at the anode, oxidation will take place, and that's where the chloride ion will undergo oxidation according to this half equation right here. And therefore what you're going to see formed at the anode are bubbles of chlorine gas, which will be directed from it and collected elsewhere, right? So that's basically what happens in the case of the electrolysis of molten sodium chloride. And then over here, it's basically the same thing with the difference being, well, this is molten sodium chloride too, but this could also happen in the case of an aqueous solution, right? If you had aqueous sodium chloride, the same thing will happen. The chloride ions will be oxidized at the anode, the sodium ions will be reduced at the cathode, and therefore you're going to have the formation of chlorine, gas, and sodium metal formed in each case. And I should correct myself. In the case of an aqueous solution, this will not happen. We're going to say more about that later on. So let's just stick to the fact that this is a molten solution of sodium chloride, right? So that's what happens when you electrolyze a molten form of sodium chloride. And this is true for any ionic compound. You basically will have the breaking up of that particular compound into its constituent elements, and therefore you can collect them afterwards, all right? So that's basically what's involved in electrolysis. Now, in an aqueous solution, which is what I mistakenly referred to in the previous diagram, in this case, they add a small amount of sulfuric acid, which allows for greater conductivity of the solution. And things are a bit different when it comes to electrolysis of water in this case, right? So this is a very dilute solution of sulfuric acid. What happens is, and for those of you, by the way, who are in my lab, you'll be looking at something like this happening, because what happens in the case of the electrolysis of water is the water will undergo oxidation according to this equation right here, right? So therefore, what you'll have is the formation of oxygen gas being formed at the anode, right? At the cathode, you're going to have reduction, excuse me, of the hydrogen ion, right? So the result will be the formation of hydrogen gas, right? So therefore, you're going to see bubbles of H2 gas formed at the cathode. And this is basically a picture showing you the actual experiment. And you'll notice that the ratio of hydrogen gas collected compared to the oxygen gas is roughly 2 to 1, which comes as no surprise, because of course water is made up of 2 equivalents of hydrogen to 1 equivalent of oxygen, right? So that's basically what happens in the case of the electrolysis of water. And again, it's a redox reaction where the oxidation will take place at anode to form oxygen, and the reduction will take place at the cathode to form hydrogen, all right? Okay, so let's talk about some quantitative aspects of electrolysis, right? So what we're looking at is how we can calculate, for example, the amount of a particular substance being formed at either an anode or a cathode based on the amount of electric current being used, right? The first thing you would have to do, let's say you're given a problem of that type and you're given the current and you're given the time at which, for which the current is run. The first thing you have to do is calculate the amount of charge, and the amount of charge is calculated using this equation right here. the charge measured in coulombs, which I think, if I remember correctly, I introduced that unit to you the last time, right? So charge measured in coulombs is equal to the current, which is measured in amperes, multiplied by the time in seconds, right? So that's the first thing you have to do. You have to calculate the charge in coulombs, right? And then you have to divide that charge by Faraday's constant. Now, if you remember, Faraday's constant is the amount of charge that is carried by 1 mole of electrons, right? So basically, once you get the charge and you multiply by Faraday's constant, then you're going to get, or divide by Faraday's constant, I'm sorry, then you're going to get the moles of electrons. And then based on the balanced half equation for the reduction or formation or oxidation of a particular species, then you can determine the moles of the substance that is either formed or reacting at a particular electrode. And then, depending on the nature of the question, you could be asked, for example, for the molar mass of the substance or the ideal gas of, or the volume or whatever, then you'd use the molar mass or the ideal gas equation if you're asked to find the grams or liters of product. So it all depends on, it all depends on, the nature of the question and the type of information that is provided to you about the question, all right? But this is essentially the flow chart which describes how you'd solve problems involving electrolysis, all right? So let's look at one example here. This question says, how much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amperes is passed through the cell for 1.5 hours, all right? So basically you have to identify the reaction that will be responsible for the formation of calcium. Now, the anode reaction is where oxidation will take place, and that would be the equation right here. But what you really need, because you're talking about the formation of calcium, is this equation right here, the equation that will take place at the cathode, where the calcium will be reduced to form, where the calcium ion will be reduced to form the calcium solid. So this is the equation that actually we'll be using, not so much this equation, right? And you'll notice that there's a 2-to-1 mole ratio between the calcium and the moles of electrons, right? So, let's talk about, so this is the ratio that you're going to use as well, in addition to this equation right here, all right? So the first thing we need to do is find the amount of charge. They gave us the current, which is 0.452 amperes. Amperes would be the same thing as coulombs per second. We multiply that by the time, but notice that the time is in hours. So what do we need to do? We need to convert the hours to seconds, right? So we multiply by 1.5 hours, and then we multiply by 3,600 seconds per hour, all right? And that will give us the moles of electrons. But remember now, there's a 2-to-1 mole ratio between the moles of electrons and the moles of calcium. So therefore, well, before we get to that, we need to find the moles of electrons, and that's where Faraday's constant comes in. So we multiply all this that we have done so far, we multiply by 1 mole of electrons divided by 96,500 coulombs, and that will give us the moles of electrons. And then, because of the 2 moles of electrons to 1 mole of calcium ratio, we multiply by a conversion factor, which allows us to go from moles of electrons to moles of calcium, and that would be this right here, right? So this is a setup, and you'll notice that the hour units will cancel out here and here. The second units will cancel out there and there. The coulomb units will cancel out there and there. The mole of electrons units will cancel out there and there. And you'll be left with the moles of electrons, which would be this when you do the number crunching. Now, the question didn't specify whether or not you should express the amount in grams or moles. So this would be correct as far as I'm concerned. But if the question had asked for the mass, then you know what to do, right? You simply multiply this by the molar mass, which means that you'd have to multiply this by 1 mole of calcium over the molar mass, which, if I'm not mistaken, is 40.08 grams of calcium. And that would give you the mass here, which is 0.50 grams, all right? So that's basically how you do this kind of problem, all right? Okay, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Okay, next slide. Okay, so this is just some examples of electrochemistry in everyday situations. Just before I left Jamaica to come here, I had my teeth, some filling by a dentist who is no longer alive. And I remember him telling me that he'll be using to fill my cavities what he called mercury amalgam. I'm sorry, tin amalgam, which is basically a combination of mercury and tin. So this brings back not so fun memories. And eventually the filling dropped out because of basically what I'm about to describe here. Basically, erosion of the filling will take place over a period of time due to redox reactions, basically, where the tin in the amalgam here will undergo oxidation to form tin 2+, and the electrons being lost as a result of that oxidation will basically form water as a result of this half equation right here, where oxygen will undergo reduction along with H+ to form water, right? So over time, basically, the corrosion will take place, which happened in my case, and therefore I had to go back to the dentist here in the States and have that tooth removed. And of course, we could look at the standard EMF values, which would help us to predict that, this will actually take place, right? So that's basically one practical example of applying what we have learned in this chapter, all right? Okay, so that's basically it as far as this chapter is concerned. So what I'm going to do now is open up a Dropbox for this assignment. Let me see here. Oh, by the way, you had told me that there was an error. What question was it, Mr.?
Number 2.
Number 2.
Okay.
Okay, yes, I think I erroneously give you a wrong answer for K in the case of number 3, right? Or, oh, my bad. Number 2. Okay, so the answer I got when I reworked this was 2.2 times 10 to the 40. Is that correct? For
when we worked it, yeah.
yeah, 2.2 times 10 to the 40. So you guys may want to make a note of that, right?
And then when I did it again, it went to 2.2 times 10 to the 40.
Right, okay. So that's the answer for number 2 for K. All right, so please make a note of that, all right? Okay. So what I'm going to do next is start with the next topic, which is dealing with nuclear chemistry. So let me go. No, unfortunately, I could not print anything. Something went wrong with the printer this morning upstairs, so I don't know what's going on. So I have not printed any. Oh, before we do that, let's do the questions. How could I forget? Before we get to nuclear chemistry, let's do the addendum questions. So let me go back to files. And where's the addendum? Assignment number 7. Addendum, okay. How could I forget? I'm getting old. Okay, so this question says in number 1, in an electrolytic cell, the negative electrode is negative because it has, what do you think the answer is? Why would the negative electrode be negative? Because it has too many or too few electrons? Too many. Too many, exactly. So the answer here is too many, all right? Okay, chemicals that come into contact with the negative electrode is it gain or lose electrons? Gain, exactly. Right? And B, is it oxidized or reduced? If something is gaining electron, what is it undergoing? Oxidation or reduction? Reduction. Remember oil rig? Oops. Oil rig. Remember that memory aid? Oxidation involves loss of electrons. Reduction involves gain of electrons, right? So that should help you to remember. So because you're gaining electrons here, then this would be reduced. All right? And then it says here, the negative electrode in electrolysis is called the what? That is indeed correct, cathode. All right, very good. Okay, so the next part here, number 2 is asking, write the change that water undergoes or goes through at the electrode, negative electrode, the cathode. So basically, it's going to be water plus electrons. So what do you think the products are? I think I went through that. Let me see if I covered that in the PowerPoint. Oh, no, I didn't. Now, to answer that question, what you'd have to do is actually go through the table and look for the reaction, the half reaction that deals with the reduction of water. So in the interest of time, I will tell you what that equation is, or what that reaction is. That reaction is, and for those of you in my lab this morning, you're going to be using this equation here. It's going to be OH minus plus H2 would be the products. And to balance this, we're going to need a 2 here, a 4 here, and a 2. No, I'm sorry. This is going to be a 2 here, plus 2 electrons here. And I think that's it for, no, wait a minute. 2 here, so that's 4 hydrogens, 2 oxygens. Oh, okay, so that's balanced, all right? So that will be the equation for the reduction of water that will take place at the electrode, at the cathode, all right? Okay. Any questions so far? Any questions? Okay, so can I clear this? All right, let me clear this now so I can scroll down. So let's see if you can answer number 3. In an electrochemical cell, the positive electrode is positive because
it has too few
electrons. Too few, okay? Chemicals that come into contact with the positive electrode will lose electrons and be oxidized. The positive electrode is called the anode. And the change that water undergoes at the anode. Now that equation I showed you in the PowerPoint, it's going to be this equation. Let me see if I can find it. It's going to be this equation right here. All right. So I'm going to rewrite that equation here. It's going to be H2O. It's going to be H2O to form H plus O2 plus electrons. And to balance this, we're going to need 2, 4, and 4 here. All right. So that would be the equation or the reaction that takes place at the anode. And somebody says something in the chat. Oh, Aiden, well, I think you were answering a question from earlier. I take it. Sorry, I didn't catch your comment in time. I'm going to try to pay more attention to the chat. Okay, so that's the reaction that would take place at the anode, the oxidation of water to form hydrogen ions and oxygen gas, all right? And then it says in number 5, add these two reactions together and make sure that the electrons cancel out. So let me clear this here. And let me scroll down. Okay, so one of the equations that we wrote down earlier, which is the reduction equation, is 2H2O plus 2 electrons to form 2OH minus plus H2. And the other equation is the oxidation equation, which is 4H2O to form 4H plus O2 plus 4 electrons, right? So what the question is asking is for us to add these two equations together, right? Make sure that the electrons cancel out. So the only way we can make sure the electrons cancel out is that we multiply this equation here by 2. Because by multiplying by 2, we're going to get 4 electrons here. So when we multiply the whole equation by 2, you're going to end up with 4H2O plus 4 electrons to give 4OH minus plus O2 plus 4 electrons. No. Plus 2H2. I'm confusing both. So this should be 2H2. All right? And then when we add these two equations together, what are we going to end up with? The 4 electrons here will cancel out here and here. And you're going to end up with 8H2O to give 4H plus 4OH minus plus O2 plus 2H2O. All right? Or plus 2H2. But here's the thing. These two here will add up to give you 4H2O. Right? So what will happen is that these 4 water molecules will cancel out 4 of these. You're going to end up with 4 H2O. So continuing over here, you're going to end up with 4 H2O to give 4 H plus 4 OH minus. And another thing that will cancel out is that if you divide right through by 4, you're going to end up with, hold on.
I have a question.
Yes, sir.
Where did the 4 come from the 4H2O? Shouldn't it be a 2?
Where?
For the second one, because it's 4 hydrogen ions. It's the hydrogen ions.
You mean here?
Yeah, because when you have
You have 4H plus here.
but it was 4H2, wouldn't that be 8 hydrogens?
Okay, where are you talking about?
Below the line, the first line.
Oh, you mean here?
No, above.
Here?
Above.
Here?
Yeah, the 4 hydrogens. What's the 4H2? Wouldn't that be 8 hydrogens?
Yeah, there should be 4H plus.
Because 4 times H2 would be 8 hydrogens plus 4 oxygens.
Oh. Okay, that's what we're saying. So this should be, let me balance this correctly. So this should be
A 2.
2, this should be 4. Okay, so this is the equation here. And okay, hold on. Let me erase this down here. Okay, so in this case here, we add, okay, so we add these two together to get 6H2O. These 4 electrons will cancel out. And here we're going to have 4H plus 4OH minus to give, and then plus O2 plus 2H2O, plus 2H2, right? These will give you 4 water molecules, right? So let me erase this here. So basically what's going to happen is that these 4 water molecules will cancel out 4 of these leaving behind 2. And you're going to now end up with 2H2O to form O2 plus 2H2, and that would be the final answer. All right? And that's how number 5 is done. Okay, any questions about that? Any questions? All right, let me clear this. And let me scroll down. So here they're describing an electrolysis process where we'll be electrolyzing a solution of sodium sulfate. And it says both sodium and water will be near the cathode, the negative electrode. So the question is, which chemical is more likely to be reduced? All right. So in this particular case, and again, this is a situation that you'll be facing in the lab this morning that you're going to do. Basically, there are two possible reduction reactions that would take place at the cathode. One is the reduction of Na plus to form Na. And the other one is the equation that we saw before, the reduction of water to form H2 and OH minus. And again, we need to make sure that this is balanced. So basically, you're going to have two here, and two here. All right. So what you'd have to do is consult the tables to look up the standard EMF values for these reductions, right? So I did that. And when I looked it up, I saw that the sodium reduction, the EMF value for that under standard condition would be minus 2.71 volts. And in the case of the water, when that is reduced, its value is minus 0.83 volts, right? So what you'd have to do next is compare these two to see which one is higher. The one that is higher is the one that is most likely to occur at the cathode, right? So that means that this is the higher value. So therefore, the one substance that will undergo reduction under these circumstances will be the H2O. All right? So that's the answer for number 6. So that's basically how you determine which of the species will undergo reduction, right? There are two possibilities. One will be sodium, the other one will be water. You look up the EMF values for those reductions, and you'll see that it's the water that will be more likely to undergo reduction, all right? Any questions about this? Any questions? Any questions? Okay, let me clear this. And scroll down to number 7. Now, in the case of number 7, we're looking at what will happen near the anode, right? And at the anode, there are two species that will undergo potentially oxidation, but one of them would be more likely than the other. And the two species are the sulfate ion and the water molecule, right? So again, you have to look up the equation. Now, in this case, you have to be careful because you have to basically determine what the oxidation of these substances will result in. So when I looked it up, I saw that sulfate, when undergoing oxidation, will form S2O8, 2 minus, plus 2 electrons. Now, you have to be careful because when you look up the values in the table, you're going to see the reverse equation, right? But you're looking for oxidation because all the equations in the table are reduction half reactions, right? But what you want for the case of anode reactions are oxidation half reactions. So you have to flip the equation around, which means that the EMF value that you see in the table, you have to change the sign for that. So when I looked it up and I changed the sign, I see that the EMF for that standard would be minus 2.05 volts, right? And then in the case of water, its oxidation is this right here, plus 4 electrons. And when I looked up the EMF for that one, again, you're going to see the value for the reduction, so you have to switch a sign. And when I looked it up, I saw that the value is equal to minus 1.2 volts, right? So again, you make a comparison between these two, and you see that this is higher compared to this one. So that means that this is the reaction that is going to take place, which means that the chemical that would be oxidized at the anode in this case would be water. All right? So that's basically the answer for number 7. All right? Any questions about that one? Any questions? Any questions? Okay, let me clear this and scroll down. Now, in the case of number 8, this time the solution is a solution of potassium iodide, right? So the question is asking, both K plus and H2O will be near the electrode. And the question is asking which one is more likely to be reduced. So again, you'd have to consult the table, and I looked up the values for the reduction of potassium. So K plus electrons would give you K, and for water, same equation as before, H2O plus 2 electrons to give H2 plus 2OH minus. So when I looked up the value for this here, the standard EMF value for that is minus 2.93 volts. And when I looked up the EMF standard for the water, that would be minus 0.83 volts. And we compare these two, and which one is higher in value or more positive? This one. So that means that it's the water that will undergo reduction at the cathode. So that would be the answer for number 8. Now, in the case of this second part here, it says both the I minus and the water will be near the electrode. Which chemical is more likely to be oxidized? Now, unfortunately, well, let me see here, hold on. Well, not unfortunately, I can write the, well, let me clear this first. Let me clear this first, so I can scroll down. Okay, so in this case here, they provide you spaces for writing down the equations, right? So, the cathode reaction, when I minus, we do need, hold on, write the reactions of each electrode. Okay, so you know what, I have to do a similar process. Let me do it up here, right? So in the case of I minus at the cathode, when that undergoes oxidation, you're going to get I2 plus 2 electrons. So you need to balance this by putting a 2 here. And the standard EMF value, when I look that up, that would be equal to, you know what? I'm not sure if I have the correct thing here. So let me go to the table. Okay, so where's the table? Let me go here. Okay, so what I'm looking for here is the equation for the oxidation of I minus. Now remember, these are all reduction equations. So let me see where iodine is. I minus the iodine. I minus the iodine. Okay, so this is the equation for the reduction, right? The EMF value is 0.54, but we're looking for the oxidation of iodine, which is the reverse, right? So that means that the sign here will change from plus 0.54 to minus 0.54. So let me go back to the question. Okay, so for the reverse, the EMF value would be minus 0.54. Minus 0.54 volts, right? And then now for the oxidation of water, which we met before, the result would be H plus O2 plus electrons, and we need 2 here, 4 here, 4 electrons, all right? And the EMF value of that, we saw already, that would equal to minus 1.23, minus 1.23. So the question now is which one has the higher value, and that would be the minus 0.54. So therefore the answer here is that the iodide will undergo oxidation more likely compared to water, right? So basically, to answer the questions here, the cathode reaction is the reaction that we saw earlier, which would be the H2O plus 2 electrons to give 2OH minus plus H2. And the anode reaction is the one that we just discovered here, which would be 2I minus to give I2 plus 2 electrons, right? And then to get the overall equation, what do? We add them, right? And when we add them, the only thing that will cancel out in this particular case would be the two electrons. So the final answer would be H2O plus 2I minus, yes, sir?
You balance the cathode, isn't there supposed to be a two in front of the H2O?
For which one?
The cathode? Is there supposed to be a two in front of there?
Oh, yes. Yes, thank you. So this is going to be 2H2O plus 2I minus. And then on the right side, you're going to have 2OH minus plus H2 plus I2, and that would be the final equation, the overall equation. All right? Okay, somebody has a question in the chat. Where did you get the cathode equation from? And that person is being asked, that question is being asked by Kilcrease. The cathode equation is from the earlier part of question number 8, when we answered where it says which chemical is more likely to be reduced. And I gave you the two equations, one involving potassium ions and the other one involving water. And when I looked up the values, the one involving water has a higher standard EMF values. So that would be the reaction. That would be for this reaction right here. So that's where we got that equation from. All right, I hope that answers your question. Okay. All right, so that's the answer for that question. All right. Okay, the next question. Let me clear this here. Okay, again, another electrolysis situation. In this case, we're looking at copper 2 sulfate. And okay, so this is my fault. I should have provided space for you to show how this is. You can probably just write that on an extra sheet of paper, but what I'm about to do, right? So basically, it says copper 2 plus and water will be near the electrode, right? Now, the water reduction is the same equation that we have been using all along. I'm going to see if I can squeeze it over here. Let me write the copper first. The copper 2 plus reduction would be this right here, right, to form copper. And the EMF value for that would be equal to, when I looked it up, 0.34 volts, right? Now, the water reduction, H2O, plus 2 electrons to form 2OH minus plus H2. The standard EMF value for that is, again, minus 0.83, minus 0.83 volts, right? So which one is higher? The reduction of copper is higher, right? So the answer here is that it's the copper 2 plus will undergo reduction. Yes, sir.
What's the EMF value for copper?
0.34,
Thank you.
and that's positive. All right, so the answer is that copper 2 plus will be the species undergoing reduction. And then it's asking for the same thing for the sulfate. Again, my fault, I should have provided space for doing this part, so let me do it over here. So in the case of the sulfate, we saw that already, SO4 2 minus, undergoing oxidation to form S2O8, 2 minus, plus 2 electrons. And when I looked up the value for that, EMF value is, where is it? Okay, so the EMF value for that is minus 2.05 volts. And then for the reduction of water, H2O plus 2 electrons to form H2 plus 2OH minus, and you need a 2 here. And the EMF of that is equal to, okay, where is that? I had it earlier. Minus point, no, this should be oxidation. Not, I'm sorry, this should be oxidation. So the equation for that one is H2O to form H plus plus O2 plus electrons. And to balance this, we need a 2 here, a 4 here, and a 4 here. And the EMF value for the oxidation is minus 1.23 volts. All right, so we compare minus 0.205 to minus 1.23. So therefore, it is the water that will undergo oxidation, and that goes here. All right. So again, I apologize for not providing space. What you can do when you submit this is write those equations on a separate sheet of paper and attach it. All right. So the equations for the overall, well, for each electrode, one of them would be for the cathode, the copper 2+ reduction to give you Cu, and the other one would be the oxidation of water to give 4H plus O2 plus 4 electrons. And therefore we need to do the overall. Of course, we have to multiply this by 2. So when we do that, the final answer will end up being 2 Cu2 plus 2 water molecules and then on the right side, you're going to have Cu plus 4H plus O2 plus 4 electrons. No 4 electrons. The electrons will cancel out. So let me erase that.
Would it be 2 Cu?
And yes, you're right. This should be 2 C's, right? And that would be the overall equation for this reaction, all right? And that's the answer for number 9. All right, any questions about this? Any questions? Any questions? Okay, let me clear this here. And let me scroll down. Okay, so the next question, number 10, it says silver plating occurs when electrolysis of silver sulfate solution is used because silver metal is formed at the, what do you think? Will silver be formed at the anode or the cathode? Now remember, silver is positively charged. So what will it be attracted to? Which electrode will it be attracted to? Cathode. Exactly. So the answer here will be the cathode. All right. And then it says this is the plus or minus electrode. So which one is going to be? Minus. And the reaction at this cathode is, so I think they're asking for the equation. So what would be the equation? It's silver ions plus what? No. SO4 2 minus will go to the anode because it's negatively charged.
Oh, yeah.
The question is asking what it would be the, basically what's the reduction reaction that would take place? The reduction half reaction that would take place at the cathode.
Be an electron.
An electron, and that would give you silver. So that would be the equation that would take place at the cathode. All right? Okay, any question about that? Any question? All right, let me clear this. And let me scroll down. And I think this would be the last. Oh, no, 2 more questions. Okay. So this question says, so this is where we're going to get into some quantitative stuff, right? It says if a cell is run for 200 seconds, so that's the time in seconds, with a current of 0.250 amps, how many grams of silver will be deposited? So we're going off the same equation from the first part. So let me just rewrite that here, right? That's the equation we're using, right? So the first thing I would do is I would take the 0.250 amps, and by the way, amps is the same thing as remind myself of something. So amps would be the same thing as coulombs per second, right? So we need to multiply that by the time, which is 200 seconds. And then we need to multiply that by 1 mole of electrons over Faraday's constant, right? So that will give you the moles of electrons. And then based on this equation here, for every 1 mole of electrons that is produced or that is used, you're going to get 1 mole of silver, right? So far, the Coulomb units will cancel out here and here, the seconds will cancel out here and here, and the moles of electrons will cancel out here and here. So the next step, because the question is asking for how many grams of silver, we need a molar mass of silver. So what's the molar mass of silver? Can somebody look it up for me, please? Or read that in?
7.868.
107.868 grams per mole of silver, and that's it. Moles of silver will cancel out. So let's see what this gives. 0.25 times 200 divided by 96500 times 107.868. And according to my calculation, this works out to, when rounded off to 3 sig figs, 0.0559 grams of silver. And that's how that is done. All right. Any questions about this one? Any questions? Okay, so let me clear this and scroll down to the last question. So the last question, it gives you the current, it gives you the time in hours. So we have to do some conversion as far as that is concerned. And it tells you that the results of that electrolysis is a decomposition of 0.250 moles of the metal at the cathode, right? Or decomposition, that should be deposition. Okay, so you may want to make a note of that. There's no decomposition. That should be deposition. I don't know where I got this question from. Anyway, so the question is asking for the oxidation state of the metal in the molten salt. So the oxidation state will be +1, +2, +3, whatever. That's what you need to find. So basically what I would do first is write down an equation. X, n to the plus charge, plus n electrons to give X, right? So basically once we find n, then we know what the charge is, right? Now, let's start off with looking at what we have here in terms of the numbers. We have 10.0 amperes, right? And in fact, let me again represent amperes as coulombs per second. So coulombs per second multiplied by the time. What's the time? 2.00 hours, but we have to convert that to seconds. So that would be 1 hour down here and 3,600 seconds above. And then we have to multiply this by 1 mole of electrons and Faraday's constant down here. Oh, wait a minute. Yes, 96500 coulombs, right? So this will cancel out with that. The seconds will cancel out here and there. The hours will cancel out here. So you're going to get moles of electrons as a result of that. So let's do the number crunching. 10 times 2 times 3,600, and then divide by 96500. And the answer you're going to get here would be 0.746 moles, 0.746 moles of electrons, right? So how do we determine N in this particular case? We have the moles of electrons and we have the moles of the metal. The moles of the metal is 0.250. So if you look at this equation here, the mole ratio between X and the moles of electrons will be equal to N. So therefore we can say that the moles of X, the moles of electron divided by the moles of X would be equal to N. So the moles of electrons is 0.746 moles divided by the moles of the metal, which is 0.250 moles. So when I do that calculation, 0.746 divided by 0.250, you're going to get 2.98. And since N must be an integer, we can approximate that to 3, right? So therefore, the charge carried by the metal will be 3 plus, or plus 3. And that's it. And that's basically how that will be done. All right? Okay, any questions about this particular question? Any question? All right, so what I'm going to do is, I'm going to create a Dropbox for this one. Let me clear this first. And let me close this. Go to no, not announcement. Assignments. And this is assignment number 7, right? Put this up. Okay, so today is the 2nd. Let me get it right here. Okay, of March. And I'm going to make it with you on the 4th at midnight. So let me do this. Okay, so it's available from today, which is the 2nd, to the 4th. Okay, so it's published. All right, so you can upload this assignment when you have completed it into Canvas. Make sure you do so by Friday. All right? Okay, I don't think we have enough time to start the next chapter, so I'm going to call it a day. So I'll see you guys on Monday. And on Monday, we're going to start nuclear chemistry, which should be some fun to deal with.
Chemistry's like the final module, right?
I'm sorry?
Nuclear chemistry is the final, like.
No, the final one will be organic chemistry, just some introductory stuff. That should be relatively easy, and that's it. And then what we can do, we can discuss this. We can discuss whether or not you guys want to do the final exam before the final period. If you want to, that's up to you guys. I guess I'll have to put that to your plate. Because some people might prefer to have the study time. So it all depends on you guys. Because I think we should be finished early. Okay, oxidation of the anode plus, yep, that's correct.
This one. AG would
See
be
how that
reduced.
All right. What's that?
AG plus would be reduced.
Oh, that's based on the question before, right?
No, let's see. Yeah.
Oh, the pH of the solution. No, but they're saying zinc chloride.
And then it says, the silver.
The bromothymol blue is yellow in an acidic solution and blue basic solution, green in neutral. A current is passed through the solution of zinc sulfate. A silver substance, well, it's not talking about silver, it's talking about the zinc. It looks
Okay.
shiny, that's what they mean. They probably shouldn't have used that word, to be perfectly honest. But what they're asking for is, okay, so what has been oxidized and what has been reduced? The zinc. Because the zinc plates out on the cathode.
HY would be oxidized,
Mhm.
zinc, and it would be Zn plus.
Zn would be oxidized, not Zn plus, because when it's oxidized, it forms Zn plus. You see what I'm saying? So you just say zinc. Yeah,
And then is zinc, and then which one would be reduced?
the zinc would be, oh, my bad, hold on. Zinc 2 plus would be reduced and would form zinc. I told you the wrong thing.
And then the water would be
And
oxidized.
the water will be oxidized according to the equation that I showed you in class just now.
Okay.
That's
That's LH
mhm.
and then OT.
Okay, you guys out there in Zoom, I think I will be signing off now.